Let's get started. So in this chapter, we'll study Gauss's law. So this is a theorem that allows you to calculate electric fields. So it will allow you to calculate electric fields for symmetric charge distributions. Okay, we'll come to that in a second. So for instance, let's first define the problem. Okay. So here is the big picture. Okay, so this is, we're dealing with the subject of electrostatics, and what that is you'll have a bunch of charges that are stationary, and what we want to know is the effect these guys will have on your pet charge. Okay, so let's say here is your charge, and we want to know what the effect of these guys is on your charge. Well, how do we figure out the effect of these guys on your charge? What you have to know is what is the electric field at this point. Okay, so if the electric field is at that point, the force on your charge is your charge times the electric field. Okay, so you're interested in how your charge will behave no matter where you place him. So what is it that you want to know? You want to know the electric field everywhere. Okay, so that's the big problem. Do you guys understand that? So for a given charge distribution, for this given charge distribution, you want to know the electric field everywhere. All right, let's see how we'll calculate this. Okay. So let's say we want to calculate the electric field at this point. The electric field due to this guy, by the way, from a point charge, the electric field is given by KQ by R squared. Okay, so the electric field due to this guy will be in this direction, E1, that vector. Due to this guy, it'll be in this direction, E2. Due to this guy will be in what direction? In this direction. Okay, so E3 due to this guy will be in that direction, E4, and due to this guy in this direction, E5. Okay, so to find the electric field at this point, you have to calculate the magnitudes of all these directions, and you have to add up all these vectors. And then you'll get the net electric field at this point. And then are you done? No, that's just one point. And then you have to calculate the electric field in here, electric field here. And pretty soon you'll quit doing physics. All right? So, but Mr. Gauss comes to your rescue. Okay? Mr. Gauss gave us a theorem to calculate the electric fields, except that, even Mr. Gauss can't help you with this, You just throw up your hands and you don't calculate the electric field for this distribution. Okay? So Mr. Gauss will help you calculate electric fields for distributions like this. Okay, if you have a straight line distribution, uniform distribution that's infinite, Mr. Gauss will let you calculate the electric field. Okay, he'll tell you what the value of this electric field is. If you have, and these are real life situations that you'll encounter. So let's say Let's say we smear this wall evenly with positive charges and this wall evenly with negative charges. Mr. Gauss will tell you how to calculate the electric field in this room. And this happens in capacitors, in parallel plate capacitors. You'll smear one plate evenly with positive charges and the other place evenly with negative charges. And you want to know the field in between this. Okay. So Gauss's law will be useful in many situations. But anyway, Mr. Gauss gives you a theorem that allows you to calculate the electric field everywhere for symmetric charge distributions. Okay. And I'll show you the 3 or 4 situations where we'll apply. But again, so here's an infinite sheet of charge where the charge is evenly sprayed. Okay? And Mr. Gauss will allow you to calculate this electric field. He'll allow you to calculate the electric field in this half of the universe and that half of the universe. Now, if there is any slight kink in this sheet, then you can't calculate it. It has to be a symmetric distribution. Let's say here's a styrofoam ball, and you evenly smear it with charges. Mr. Gauss will allow you to calculate the electric field everywhere. Okay. Again, there's that infinite sheet. Here's an infinitely long line charge, uniformly distributed, and Mr. Gauss allows you to calculate the electric field. So I showed you for a sheet of charge, for a spherical distribution of charge, for a linear charge density. And then for other charge distributions that are made up of these guys, you can calculate the electric field. So those are the 3 situations I'm showing you. Okay? All right, so let's see what Mr. Gauss has to say. Okay, so do you guys understand? We are calculating the electric field due to uniform charge distributions, which are symmetric. Okay, that's what Mr. Gauss will let you do. All right, so that's what Gauss's law is about. Okay, so Gauss's law is convenient for calculating electric fields of highly symmetric charge distributions. What the law does is it relates electric fields at a point on a closed Gaussian surface to the net charge enclosed within the surface. Okay, so what this theorem does is the following. Okay, so let's say here's a surface. Okay, so let's say the electric field on this surface is this E, and there's the small area element. Okay, we'll associate an area vector with an area element. Okay, and the area vector is, the direction of the vector is perpendicular to this surface, and the magnitude of this area vector is just the magnitude of this area. Okay, so we are defining an area vector. Okay, again, the direction is perpendicular to the area, and the magnitude of the area vector is just the area. Okay, you take this dot product, E dot A, and you do that for every little piece and sum it all over. That is what is called a surface integral. Okay, I don't know, you'll probably do this in Calc 3. Okay, so you're taking the surface integral of this electric field vector at all locations. And what Mr. Gauss says is, that's the Gauss's theorem, that surface integral is equal to the charge inside divided by epsilon. Whatever is the total charge inside divided by epsilon. All right, see, here's the beauty of this formula. Okay, there is that. Okay, so let's say that's the charge inside. So Mr. Gauss says this is called the flux. The surface integral is called the flux over an enclosed surface. That circle means it's an enclosed surface, not an open surface. is charge inside divided by epsilon. So here's one thing you can see right off. Okay, so that integral over this surface is equal to charge inside divided by epsilon naught. You can do that integral over this surface. What is the value you get? The charge enclosed is the same, so you get the same thing. You guys understand? What is the integral over that surface? Same thing. All right. That's Gauss's law. Okay. And we are going to use that to deduce various things, and you'll learn some neat things. Okay. So let's go ahead and get started. So it relates electric fields at points on a closed Gaussian surface to the net charge enclosed within the surface. Okay. Okay. First, we'll define material flux, just so you have something in mind. Okay. So let's say this is a river flowing, and what these vectors are this is the vector field. It's telling you the velocity of the water at any given point. And so when they draw arrows like this, what does this mean? What are they trying to tell you? The velocity of the water is constant. Okay, it's a uniform vector field. All right, so here is this water flowing, and it's a steady flow. And what you want to ask is the following. So let's say you put a ring there like that, perpendicular to the flow. You want to ask how many gallons are flowing a second, or how many gallons of water are flowing a minute. Okay, and that's a very valid question, and that's called material flux. Okay, the flow rate is what you want. And if you hold this perpendicular, the flow rate is just A times V. Area of this ring times the velocity. Okay, so if the area is in meters square, the velocity in meters per second, what you'll get is AV will be meter cubed per second. Okay, volume per second. So that gives you the volume flow rate. Some number times. Okay. Now, what happens if this area is held perpendicular, is held like that? What is the flow rate now through this ring? What is the flow rate if you hold the ring edgewise? 0. Okay. So as you change the angle from here to there, it's going from 0 to the maximum value. Okay. So when you hold it at an angle, it turns out so now we'll define this area vector. The area vector is the magnitude of this vector is just the area of this ring. Okay. And the direction of the area vector is perpendicular to this area. Okay. So now if you hold the area at an angle theta to the flow, what matters is this component of the area. Okay. And that component of the area is A cosine theta. Okay, so this angle is theta and this angle will be theta. So this component of the area is A, this angle is theta, is A cosine theta. So now the flow through this area is AV cosine theta. And now you can see why we define this area vector. So if you define the area vector like that, now you can write flow rate as the velocity vector dotted with the area vector. Okay? And that's why we define an area vector. Okay. And when the area is like this, the angle between the velocity vector and area vector is 90 degrees, and cosine of 90 would be 0. Okay. All right, so the flow rate is V dot A. All right, in the last chapter you learned that if you have an electric field in a region, the way electric field is a vector field, and if the field is stronger here, the way you indicated the field was stronger was by drawing more lines. the density of lines was higher. A weaker field was indicated by a lower density of lines. So this is telling you it's a weaker field here. This is telling you it's a stronger field here. Okay. So just like we defined the material flux, we'll define electric flux. And electric flux will be, you can think of it just as how many lines, electric field lines are penetrating this area. Okay. And so the number of lines penetrating the electric field is, the field strength is the number of lines per unit area. And so the number of field lines penetrating this area is E times A. That tells you how many lines are penetrating this area. All right. What if the area was like this? How many lines are penetrating this area? Zero. Okay. So again, we'll define an area vector, just like in the previous case. And so the electric flux will be E dot area. Okay, so for this area, there's the area vector, and there's the area vector. And so what is relevant is this component of the area. So A cosine theta. Okay. So the electric flux is denoted by phi, capital Phi, the subscript E telling you that we're talking about an electric flux. And so that's the number of electric field lines penetrating this area. Okay, in a later chapter, we'll talk about magnetic flux. So that's why we're building this notation. Okay. So the subscript E tells you now we're talking about electric flux. Okay, so the electric flux is the number of lines penetrating an area, is the electric field dotted with the area vector. All right, so now let's come to this guy. So let's say there's electric field in this region like that. What you want to do is, so this is an enclosed surface, this is a closed surface, and we want to calculate the electric flux through this surface. Okay. The rule is the following: if there's a field line going out of the area, it's considered positive. If there's a field line going into the area, that's considered negative flux. Okay, so that's the rule for counting. All right, so what Mr. Gauss will say is, so you calculate the flux for this area, which is E dotted with that area. So E dotted with that area. And you guys know what the area vector is. The direction is perpendicular to the area, pointing outside the surface, and the magnitude is just the area of that vector. And you do that and add up. Its magnitude and direction are the same everywhere. Okay, that's what we mean by uniform electric field. That's what we would mean by a uniform steady flowing river. You can measure the velocity of water anywhere. The speed will be the same and the direction will be the same. Okay. All right, let's calculate the flux through this cube. Okay. And the flux through this cube, this area and the electric field, they're parallel to each other. So the flux through this is just the electric field times the area of this face, which is that. The electric field times the area of that face. Through this face, the field lines are going in, the area is that way, and cosine of 180 is -1, so through that face, the flux is minus EL squared. And through the side four faces, the electric field is, the area vector is perpendicular to the electric field, so they are contributing 0. So the total flux through the entire object is 0. Okay. And so Mr. Gauss will tell you that, okay, so the flux through Gauss's law says the flux through an enclosed surface is the charge inside divided by epsilon naught. So from here, you can tell that there's no charge here. So here is what you can conclude. So this is the kind of neat stuff you can conclude. If you have a uniform electric field here, the only way, so let's say in this room, you have a uniform electric field everywhere. So now that you know Gauss's law, this can only be possible if there are no charges here, anywhere in here. If there was a charge, you couldn't have a uniform electric field like that. So you can walk around with a box everywhere in this room. If the flux through that box is zero, that means there's no charges anywhere. All right, so then the question becomes, how do you create this uniform electric field? You can create this uniform electric field, you'll see in a little bit, by smearing that wall with even positive charges evenly, and this wall with negative charges evenly. And that's what happens in a capacitor, in a parallel plate capacitor that you'll learn about in the next chapter. Okay, let me show you a little applet for that. I'm looking for the capacitor applet. All right, so here's a parallel plate capacitor. You'll learn in the next chapter that the capacitor is just two pieces of metal. And so you can take an aluminum sheet here. Here's another aluminum sheet connected to a battery. And here, see, the electric field lines between the plates are constant, uniform. Okay, so here is a situation how you create them. If there was any charge in between those, that field wouldn't be uniform. Okay? So we create these uniform fields all the time. Okay. So here, let's charge this guy. So this is your, the flash bulb in your cameras. This is how it operates. So your battery in the camera will charge a capacitor. And so what you have done is you've transferred energy from here to there. And now when you want to take a picture, there you go. Okay, this bulb, what did this bulb do? If at night, if there's no other light, it'll turn this darkness into daylight. That bulb will light up like 200 100-watt bulbs. So what was the purpose of this circuit? Okay, what did you do? You transferred energy from here to there. Why did you do that? This fella releases his energy very slowly. So what you did was you put, this is like money in bonds, you turned it into cash. And this guy, a capacitor, will release his energy very fast. This guy takes hours to release his energy. This guy will release it in a millisecond or a microsecond or a nanosecond, whatever speed. Huh?
Spends the cash.
Spends the cash. All right, so any application where you want energy very fast, that's what happens. So in supercharged cars, when you want to take off from a red light, they store energy in capacitors. Okay. All right. And a lot of, anyway, we'll learn about all of that. All right, so let's get back to Gauss's law. Hey, you guys okay with me finishing this lecture? I'll just go over the stuff a little quickly. I don't want to. Right. So Mr. Gauss tells us. Okay. So here's an enclosed surface. So if you calculate this surface integral, that's called the electric flux. And Mr. Gauss tells us that the electric flux is equal to the charge inside divided by epsilon naught. Epsilon naught is just this constant. It's called the permittivity of free space. Okay. And so if you calculate, you see, if you calculate Gauss, that flux through this surface, there's a positive charge inside, so the value of this surface integral will be positive. Okay. And you see there are lines coming out. If you calculate it around this guy, the charge inside is negative, and you see all the lines are going in, so the flux will come out negative. Okay. What about if you calculate this flux about this guy, surface? Well, if these two charges are equal, there's an equal number of lines coming in and going out, so the flux will come out to be 0, because the charge is 0. Okay. How about this guy? There's no charge inside. The flux around this surface will be 0. There's equal number of lines coming in and going out. Okay, so that's what Mr. Gauss tells us. All right, what this does is it just from a point charge, the electric field at this point is given by this expression, and this uses Gauss's law to prove that. Okay, so whenever you use Gauss's law, the trick is to do this integral, and this integral can be only done in very symmetric cases. Okay, so I'll illustrate this. Okay, so let's say this is a point charge. The Gaussian surface you want to draw is a sphere centered around that point. And now from symmetry, the field will have the same magnitude, and it'll be perpendicular to the surface. Okay, so this integral will be just the magnitude of the electric field times this surface area. Okay, so this integral is just the electric field times this surface area. Okay, and that's equal to the charge inside divided by epsilon naught. So the electric field is Q. The electric field is Q divided by 4 pi epsilon naught r squared. And 4 pi epsilon naught Ka, the Coulomb's constant, is related to the permittivity of free space like that. Okay. So that's the electric field due to point. Again, the key point was you could do this integral and you're not doing anything. You're doing this integral for very symmetric case. If you draw a Gaussian surface where it's centered at that point, you know that the electric field has the same magnitude everywhere, and it's pointed away from the center. And so this integral was just E times 4 pi r squared. Okay, so that's the trick that's employed. Okay, again, for a spherically symmetric charge distribution, so you can do this if you take a styrofoam ball, you can smear it with charges evenly. Force of gravity on you is only due to this guy. All this guy, the force, net force on you due to the outer shell is 0. Okay. All right, so just like that, if you have an uniform charge distribution, the electric field is at this point is only due to these guys. These guys have the net field due to this guy is 0. So at the center, the field on electric field is 0, and as you go outward, this magnitude of the electric field increases. It's maximum at the surface, and then as you go further out, the strength of the electric field decreases. Okay? And the strength of the electric field decreases as if this is a point charge. That distance r is from there. Okay, so outside this spherical charge distribution, this charge distribution is behaving like a point charge. just like gravity. So this is Earth. If you're outside, the Earth might as well be a point. The electric field, the gravitational field on you in the International Space Station is the same as if the Earth were a single point. Okay. So what we are saying is, if you're here in the International Space Station, and if somebody turned Earth into a black hole, your orbit would not change. Okay? The gravitational field, once you're outside the Earth, it will remain the same, no matter what you do to the Earth. Okay? All right, so this is, if you have an infinite sheet and you spray it uniformly, so this is a plastic sheet, again, and you spray it uniformly with charge, the field here, okay, so now what we'll do is we'll draw this Gaussian surface, okay? So we'll draw a cylinder of circular cross section, and the cylinder is spanning the sheet, okay? So now, if this is an infinite sheet without any kinks, if there's an electric field, this electric field is here, it's pointing this way and it's pointing like that, okay? And you can imagine, so now I'll draw a side view like this. So the sheet is infinite. Here's the electric field. Let's say it's like that. What would be the electric field here? From symmetry, you would see that it has to have the same magnitude and pointing in the perpendicular to the sheet. Now, we don't know if the electric field is going to depend on distance. As you go out further, you might think that it might become weaker, but we don't know that yet. Okay, so we'll find out in a second. Okay, so now what we'll do is we'll draw a Gaussian surface like this. So this will be our Gaussian surface. So this is that Gaussian surface that we drew, that cylinder. This is the cylinder we drew. Okay. The flux, the sides are contributing 0. The sides are contributing 0. Only these two faces contribute. And it's the electric field times the area. Okay. And E times area plus E times area. That's 2 times E times area. And that's equal to the charge inside. Okay. And the charge inside is the surface charge density, that's what sigma is, times the area, divided by epsilon naught. And so the electric field, so again, 2 times E times area equal to sigma times sigma. So the electric field, and from an infinite sheet of charge of uniform density, the electric field is this. Here's the neat thing about it. There's no distance information. So the electric field at this point has the same strength as this point, has the same strength in the neighboring galaxy. All right, so what we're saying is the electric field from a uniform sheet, infinite sheet, is sigma by 2 epsilon naught in this half of the universe, and it's is sigma by 2 epsilon naught in this half of the universe. So from an infinite sheet, we've calculated the electric field in the entire universe. Just like that. Okay? That's what Mr. Gauss allowed you to do. Of course, this is for a flat, uniformly charged sheet. Soon as there's a little kink, that argument goes up. Okay? If you had an infinitely long wire uniformly smeared, the electric field is pointing away, and the electric field is 2 times the Coulomb's constant. This is the linear charge density, the charge per unit length divided by R. Okay, that's what Mr. Gauss says. Now here's a neat thing. Okay, how can I produce a uniform electric field in this room? How can I produce a uniform electric field in this room? Very good. So if I want to produce a uniform electric field in this room, what I do is smear this wall with positive charges and this wall with negative charges. Okay, now what we'll do is the following. Okay, so we'll go bring a piece of copper metal and place it like that. Okay, bring it inside the room. What is the electric field inside the copper metal? The same as the room. Okay, what happens is if you bring a piece of metal, so this electric field, copper metal has plenty of free electrons, and those electrons respond. So the instant you bring in, there will be an electric field, but the electrons will respond to them, and the electrons will collect here. And then you'll have a positive charge here. These guys induce this electric field. This electric field cancels that electric field, and the net electric field inside here will be 0. What's that? Oh no, I haven't come to the punchline yet. How fast does this happen? In 10 to the minus 18 seconds. So you bring a piece of metal in there, instantly the electric field goes to 0. Okay? Well, why do we care about this? Okay, so let's say here's a metal box. You have if you get a cell phone signal, a cell phone signal consists of electric fields and magnetic fields. You have an electric field here. You have a metal box. Inside the metal box, this signal doesn't penetrate. The electric field is 0 in there. Okay. So if you have a building which has a lot of metal in its structure, you don't get a cell phone signal. Okay. All right. So inside a metal, in a static, well, even if the electric field is changing, as long as it doesn't change faster than 10 to the minus 18 seconds, the electric field goes to 0. Okay. If you have a piece of metal and if you put in a bunch of extra charges, Gauss's law tells you all the charges will reside on the outside surface. And they will distribute such that the potential is even. Okay. Even if it has a hole in there, all the charges will be on the surface, not on the inner surface. Okay. All this is so to make sure that the electric field, so the driving forces inside the metal, the electric field is 0. All the charges redistribute such that the electric field is 0. Okay. So here's that metal Faraday's cage that I talked about. Okay. You can have this electric field as strong as you want outside. How strong is the electric field outside? Can you tell from the picture?
3 times 10 to the 6.
Very good, my friend. Very good. It's greater than 3 times. Anytime you see a spark, the electric field is 3 million volts per meter. What is the electric field inside? 0. Okay, I got to experience this last summer. I got to find my picture with me inside there. Okay, so this is a Faraday's cage. So when lightning happens, okay, your car is a metal cage, and so one of the safest place is to be is inside your car. Okay, what this shows you is, okay, so here's a metal sphere. If you put a negative charge here, there'll be electric field inside. Okay, now this is interesting. So, okay, so again, the charges are induced on this metal sphere. The charges induced are such that they want to make the electric field here zero. Okay, and so there's positive charges induced here. And it's interesting, the center of this positive charge is right on top of this positive charge. And if this is 10 units of negative charge, this adds up to 10 units of positive charge, and this adds up to 10 units of negative charge. Okay? But the outside charge distribution is uniform. So if you hide a negative charge inside a metal sphere, this outside field is uniform. You don't know where the negative charge is located. There's no way of knowing where the negative charge is from this field. Okay. All right. So here's a metal object with a conductor with excess charge. How do the charges want to distribute? The positive charges want to be as far away from each other as possible, so they go as far away as possible. But when you have sharp corners, okay, the charge density is higher near sharp corners. The electric field is sigma by epsilon naught. Sigma is the charge density. So the electric field, since the charge density is higher here, the electric field is higher here. So if you have a metal object, the electric field is weaker near flatter surfaces and stronger near sharper surfaces. All right, well, why do we talk about this? So here's a metal, and you see the electric field is sharper here, stronger here. Well, why do we care about this? Okay, let's say for most people, one of your biggest investment will be your house. And here's a thundercloud. If a lightning strikes your house, there goes your investment. So what do? You put a sharp metal object there. The electric field is strongest here, and once it gets beyond 3 million volt per meter, it'll conduct lightning away from here without harming your house. Okay, so that's what lightning conductors are. Okay. Sharp metal objects. All right, I'll mention this solid angle. Okay, so this is a proof of Gauss's law. This is a proof of Coulomb's law. Okay, so here's a circle. You guys have you encountered solid angles? Have you heard of solid angles? Steradians? No. Okay. You will. Hopefully you will. Oh, it doesn't matter. Here you're going to listen. Here, find out now. Okay. So here's a circle. Here's how you define radians. This is the arc length. This is the radius. The angle in radians is S over R. So this is for a circle. Okay, now let's do a sphere. So let's do a basketball. Okay, we'll generalize this. So radians was arc length divided by that. Now we'll define a solid angle. And this is denoted by omega. It will be area divided by r squared, r. So the solid angle subtended will be area divided by r squared. R is the radius of the sphere. Area is in meter square divided by r squared, gives you a dimensionless quantity. Okay? So, and that is the solid angle. Okay, so think of a cone. The angle inside the cone is a solid angle. All right. What is the total angle in a circle? 2 pi radians. Okay, 2 pi radians. Let's find out what's the total angle inside a sphere. What is the surface area of a sphere?
4 times.
Very good. Thank you, David. 4 pi r squared. And so the total solid angle is 4 pi steradians. This is called radians. A solid angle is called a steradian. The units are, okay. Yes, so you can define solid angles for as area over r squared. And you can keep extending this. So this is a two-dimensional two-dimensional surface embedded in 3 dimensions. You can have a 3-dimensional surface embedded in 4 dimensions. 4-dimensional surface embedded in 5. Okay? So you can keep defining angles like that. Okay, so this is solid angle. All right, we'll stop here.